Welcome to Building the World of Grid, a virtual GDC talk. I'll pause here briefly so anyone who wants to can read the legal notices, and then we can move on to the talk itself. Today we'll be focusing on the PC build of GRID 2019, developed by Codemasters in the UK. Your speakers today will be myself, Lee Davis, a developer technology engineer working at Intel on the game team, which stands for Graphics and Multi-Core Engineering. I've worked at Intel for 13 years. Prior to that, I worked at several games development companies in the UK.
And me, David Amer. I've been working in the games industry for about 16 years now. Around 6 years ago, I started my own company, and we specialise in providing graphics and performance know-how. During this time, I've worked with a number of AAA game studios, and I'm here today to talk about some of the work I've been doing with Codemasters.
Today's talk will be split into multiple sections. I'll do a brief introduction of the game before handing over to David, who will talk about modernising GRID and the work the studio did on porting over to DirectX 12. I'll then discuss variable rate shading and how it's applied to the GRID engine, before handing back to David, who will talk about some R&D that Codemasters have been doing on multi-adapter. And finally we're complete with a summary. First, a brief introduction for anyone not familiar with GRID. GRID is a racing title, as is hopefully obvious from the image, developed by Codemasters in the UK. It is the latest in a franchise that started with Race Driver, moving through GRID, GRID 2 and GRID Autosport. With GRID 2019, Codemasters took several goals for this version of the franchise. They wanted to bring the latest graphical enhancements to GRID. They wanted to improve the visual quality of the lighting, including bringing in research on global illumination techniques. They wanted to move away from pre-baked solutions to more dynamic systems, allowing a wider variety of environments to be implemented. At the same time, they wanted to continue to improve scalability, allowing GRID to be supported on everything from a 15-watt laptop all the way up to a high-end PC. As with any updated version of the franchise, there was a drive to improve the gameplay experience with more dynamic and realistic environments, including the physics simulation. One of the main ways to do that was to actually move to DirectX 12 for both the PC and the Xbox. This would allow explicit control over things like async compute and leverage high-end new hardware features such as variable rate shading, which we will talk about later in this presentation. GRID is built on Codemasters EGO engine. This is a proprietary engine that's developed in-house and supports the F1, GRID and Dirt franchises. It's designed to be scalable and heavily multi-threaded, and it's designed to scale across a variety of hardware. It can be configured in multiple different ways. For example, F1 2019 uses a mix of forward plus and deferred rendering, while GRID uses just a forward plus lighting model. The EGO engine has been heavily optimized for the consoles, and the move to DirectX 12 allows for an increased shared codebase, with heavy use of things like asynchronous compute shaders for some of the more advanced lighting features. With that, I'd like to hand over to David to do the next section.
I'm going to talk for a while about some of the changes that we made to modernise GRID. Perhaps the biggest of these was the decision to drop the deferred renderer in favour of using the forward plus algorithm. The forward plus algorithm has been in the engine for a while now, as it was required to render things like the cars, which have a material that doesn't fit well into a G-buffer, and transparencies, as they can't natively be handled by a deferred renderer. As well as being suitable for rendering the whole scene, it offers other advantages such as native support for multi-sample anti-aliasing, better scaling with resolution, and the ability to use custom shades on objects without worrying about bloating the shaders or G-buffer for other objects in the scene. The next thing I'm going to cover is the layout of a frame. The first thing we do is we run some compute shaders to update the global illumination system and to cull the lights against the view frustum. This is done without a depth buffer query so that it can be performed right at the start of the frame. We then render a depth prepass, and for the dynamic objects in the scene we output each pixel's velocity. We render the deferred decal buffers. These are some screen size buffers that contain material information that gets blended with the surface materials in the scene. This is used to add some detail to surfaces such as the road. We render the screen space ambient occlusion using either the Hemi SSAO or HBO plus algorithms, both of which are compute shaders and depend only on the depth buffer. We next render a set of cascaded shadow maps and combine the result using a compute shader into a full screen buffer that represents the visibility of the sun from the surface behind each pixel. Next come the environment maps. These use the lowest quality material shaders and, depending on the quality settings, can be updated across several frames. The mirrors, much like the environment maps, use the lowest quality shaders and use pre-baked light maps for most of their lighting. Both the environment maps and the mirrors turn out to be particularly good candidates for the variable rate shading, which Lee will talk about later in the presentation. Now that we have all those other buffers generated, we can combine them along with our scene data to render our main scene image. Though we're not quite done yet. We compute the static geometry screen space velocity using this frame's and the last frame's camera matrices, and add some extra detail to the scene with some approximate screen space reflections on the bonnet. We update and render the particles at a quarter resolution to save on bandwidth. These are then applied to the main scene using a bilateral upsample to preserve the edges on depth discontinuities. We finally apply some post-processing to the scene and lay the UI over the top. As I mentioned on the way through the frame, some of our workload is implemented as compute shaders. The image on this slide describes how our frame's workload is distributed. Lines above the centre are executed on the graphics queue, and lines below are done on a compute queue. Blue sections are pixel shader work, green are vertex shaders, and the yellow sections are compute shaders. We aim to execute compute shaders asynchronously wherever possible, and we actually have 2 async compute queues to achieve this. Where we can, we lower the priority of one of them, and then this queue is used for tasks that can be allowed to run for longer. This helps to avoid fighting the higher priority queues for the resources they need. These boxes should help illustrate when the async compute is scheduled throughout the frame. The green boxes represent the graphics queue, the top yellow boxes are the normal priority async compute queue, and the ones below are the low priority queue. Because the initial 2 compute shaders have no dependencies on any other part of the frame, they can be executed right at the start and happily overlap with the depth pre-pass. The shadows are heavily vertex bound, and they overlap well with the particle simulation, screen space ambient occlusion generation, and object culling. The environment map overlaps with the shadow mask generation. The main scene keeps the GPU very busy anyway, so we don't overlap anything with that. And the static geometry velocity calculation and some buffer clears overlap with the particle render. Overall, the use of async compute has offered significant speed-ups. It can save a decent number of milliseconds on consoles, and the saving on PC is certainly worthwhile too. It doesn't come for free. The work needs to be implemented as a compute shader, and it's vital that there's adequate synchronization between the queues. To benefit most from async compute, it's best to try and schedule complementary work on the various queues. For example, run a math-heavy shader at the same time as a bandwidth-heavy graphics task, or vice versa. The area that was improved was the global illumination system. The system implemented in GRID was inspired by the one in the Division and the one in Battlefront 2, but is not exactly like either of them. It consists of 3 stages. We pre-bake some spherical harmonic values at build time. We load those values and populate some volume textures with them. And finally we sample the volume textures when calculating the lighting. I'm actually going to start with explaining how we use the baked values, as the process of generating them is somewhat recursive. The first thing we do is we move the volume to the camera's position and populate it with the spherical harmonic values for that area of the world. Then when we shade a pixel in the scene, we check if it falls inside the volume. If it does, we calculate the indirect lighting by sampling the volume textures, and we also calculate the lighting for both static and dynamic lights. If the pixel falls outside of the volume, we still compute the dynamic lights, but use a light map for the static lights and global illumination. To generate the data, we must first place some probes in the world. We place the probes along the track spline, 3 on either side, with another set stacked on top. Outside of the track, we place the probes in the grid with 4 metre spacing for the first 100 metres, then 20 metre spacing beyond that. To avoid placing probes that intersect the level geometry, we voxelize the scene and then test against that to ensure there are no overlaps. At each probe's position, we render a 128 by 128 cube map and then convolve the cube map down to an L1 spherical harmonic. We then write those values out to disk in the form of 3 half 4s ready to be loaded and used. To bake the light map, we place the global illumination volume in the world and populate it with the probe data. We then use the UV atlas that our ambient occlusion baking tool generates to project the static geometry and rasterize it onto the light map. We light the geometry using a white diffuse colour and the result gets saved to disk. We then repeat the whole process again, but this time using the light map when we generate the probes. This gives us a second bounce in our global illumination values. So what does it all cost? The process involves 2 rounds of generating 100,000 probes per route per track. This then has to be done for each time of day. Fortunately, the process only takes around 4 minutes per route per track per time of day. We did look at using optics for ray trace to radiance bake, but that took more like 24 hours per route per track per time of day. There were a few things that caused us rendering related issues during the development of the game, probably the most tricky of which was GPU memory management. There were 2 things in particular that caused issues: allocating resources and making sure the allocated resources were resident on the device at the right moment. If you aren't aware, memory management in DirectX 12 and Vulkan is much more manual than in earlier APIs. They have a relatively low limit on the total number of allocations that can be made, and it's up to the user of the API to pool allocations to make sure they don't exceed these limits. Another factor that makes memory management tricky is the amount of time that it takes to allocate memory is highly variable. We've frequently seen allocations taking tens of milliseconds and even several seconds on occasions. Most things in the scene are allocated up front at load time, so this isn't very noticeable, but there are other resources that need to be created at runtime, the most significant being the texture streaming system. To remedy this, we created a system that pre-allocated fixed size blocks of memory and then placed the stream textures inside of those. We found that 256 megabyte blocks worked well. Blocks smaller than this seemed to suffer from fragmentation, and larger ones on occasion caused frame stuttering when memory got low. We found that placing large and small allocations separately helped to reduce the fragmentation we experienced without complicating things too much. When it comes to fitting the resources you need into VRAM, you'll need to make use of evict and make resident members of the D3D device. Something to remember when using them is that they're ref counted, and if calls to make resident and evict aren't balanced, then they probably won't behave the way you expect them to. It's also worth remembering that it's entirely valid for make resident to fail, and you must somehow deal with it. If it does fail, you should make some effort to free some space in VRAM and try again. GRID tries to keep memory utilisation under 80% to allow for some headroom in an attempt to prevent make resident failing at critical moments. However, this isn't foolproof because things like fragmentation can cause allocations to fail, even if at first glance they appear safe. Another thing to keep in mind when working on your residency system is that not all hardware and drivers behave the same way, and things that seem to work on one device will fail on others. As a general rule, it's good to be able to simultaneously run 2 instances of your game. This should put enough pressure on the underlying systems that any issues with your implementation will be forced into the light. As I mentioned earlier, there are differences in the behaviour of the various pieces of hardware out there. For example, evict is more of a suggestion than an instruction, and some drivers decide to occasionally ignore it. This can hide flaws in the residency code because the resources remain resident. It's crucial to get residency management correct, as a GPU accessing an evicted resource will cause a page fault and a TDR, and those are no fun at all. It could also hide performance issues related to inefficient use of evict and make resident. When it comes to tracking down TDRs, there are a few tools that can help. There are a number of vendor-specific options, but there's also now DRED from Microsoft. This helps track down where in the frame a TDR occurred because it leaves a trail of breadcrumbs in the command queue and will report the last render operation that was started by the GPU. There are a few caveats to this, but it should work as expected for most hardware configurations. DRED will also report the type of error that caused the TDR and tries to supply information about the resources that were probably involved in the error. There's a bunch of information about what DRED can do and how it achieves it at the address listed on this slide. While we're on the subject of memory, I'll talk a bit about another improvement we made to this version of GRID. We found that when we increased the resolution of the texture assets of the vehicles, they used a disproportionate amount of memory. This was because they were customizable and composited on the GPU at runtime. Because of this, they were also uncompressed, and doubling their dimensions cost almost half a gig of memory. To address this, we ported the BC1 compression code from the DirectX text library to the EGO engine. We then doubled the dimensions of the composited textures and compressed them to BC1 using the ported compute shader. This reduced the memory footprint of the new larger textures to half that of the original uncompressed textures.
Thank you, David. Right, as just mentioned, one of the areas that we wanted to tackle in GRID is pixel throughput. And to do that, we wanted to make use of one of the new hardware features that is available in DirectX 12 on modern hardware, and that's variable rate shading. Variable rate shading was introduced by Microsoft last year at GDC, and I've linked a talk for more details. The idea behind VRS was to tackle the problem that display resolution is growing at a much faster rate than pixel throughput. This is especially true for power constrained platforms such as laptops in the 15 watt range. Traditionally, what people have done is upsample the 3D scene. So render at a lower resolution, upscale, apply filters before applying the UI at native resolution. This can work very well, but there are issues. For example, if we use a typical scene here and we zoom in closely, we can see when upscaled, while the actual texturing can look quite good, things that are made up of fine geometry, such as the clothesline, start to break down. Variable rate shading tackles the problem in a slightly different way. The pixel shader invocations are run at a much lower rate, in the comparable region to doing upscaling. The difference here is the depth testing is still done at the full native resolution. So things like the clothesline actually has a much finer level of detail. This means when we finally get to the end of the scene and we want to apply our post-processing effects and do things like CMAA or a sharpening filter, there's more detail in the scene to actually process. The idea of VRS is to smartly control the rasterization rate, so pixel shading is done where it will give the most benefit. There are multiple types of variable rate shading. Intel introduced Tier 1 with Ice Lake last year. With Tier 1, the shading is done on a per draw call basis. In order to understand if we can actually use variable rate shading on a piece of hardware, the first thing to check is the OS support. It requires the May 2019 version of Windows and an SDK from that date onwards. Assuming that you're running on an updated Windows platform, then using DirectX you can query for VRS support. If VRS is supported, you can then call set shading rate to set the VRS on a per draw call basis, and that is done by promoting the graphics command list to version 5 using query interface, so the rest of the code doesn't need to change, only the points where you want to actually change draw calls. The shading rates you can set vary. There are some base shading rates which are standard 1x1, 2x1, 1x2 and 2x2, and some additional rates that has to be checked using caps bits. These go all the way up to 4x4. Currently every piece of hardware that supports variable rate shading has all the additional shading rates as well, but it's still something worth checking. I should point out at this point that changing the variable rate on a per draw call basis does come with some cost, so it's best to cache the state changes, just as you would with any other fairly expensive API call. Okay, the idea behind VRS is really about trying to preserve the edge quality of 3D geometry. For example, if we take a normal 16 by 16 triangle, that's got 136 pixel shader invocations if shaded at a 1x1 rate. By doing something like variable rate shading at a 4x4 rate, the pixel shader is only invoked 10 times, but as you can see on the image on the right, the actual edge is still as sharp as it would have been at the full rate, because the depth tests are still done with 136 individual depth tests. One thing to actually note is what happens with very small triangles. If we go down to a very small triangle that's just a few pixels by a few pixels, at a 1x1 shading rate we may have 6 pixel shader invocations. At 4x4 we still have 2. We can't reduce that any further. So as you reduce the triangle size, the benefits from variable rate shading do decrease, and that's worth bearing in mind, especially when trying to apply something on a per draw call basis inside of a scene. The first thing to actually look at when using VRS is the actual quality benefits you get, and the easiest way to do that, especially in a game where things can change from frame to frame, is to use a tool such as Intel's Graphics Performance Analyzer. Graphics Performance Analyzer will actually run on a wide variety of hardware, including platforms from NVIDIA and AMD. It does a standard scene capture where it records the D3D calls and allows you to play them back. During playback, you can actually select the state and modify it to see the effects it could have on your performance. VRS is one of the states that can be changed, and if we zoom in very closely here, you can see that on the standard sort of drop down for the shading rate, you can select all the different shading rates that are supported by the hardware you're running on. The thing to actually note is the standard metrics on the other side for the number of pixel shader invocations. As you change the shading rate, you should see the number of pixel shader invocations drop. One thing to do at this point is probably to save out the image inside of GPA. That allows you to do a direct comparison to see what changes have happened just from using variable rate shading. I say the pixel shader invocations should change. One of the things we found with Grid when we first implemented VRS was the calls went into the actual API to actually change it, but we were finding that when running the game it looked the same and performance wasn't actually changing. And when we started to delve deeper into it in GPA, we noticed that pixel shader invocations weren't actually changing. There are a couple of things that can actually cause this. The first one, especially with tier 1, things like SV coverage actually disables the VRS shading rate and forces it to 1 by 1. When using sample mask, that has to be a full mask. If you're actually evaluating at anything other than the default position in the pixel shader, then that will override VRS and reduce it back down to 1 by 1. And the one that caught us out in Grid is the HLSL keyword sample. That's tended to be used in previous versions of Grid for when doing multi-sampled render targets. Even though Grid wasn't using any multi-sampled render targets in this iteration, the keyword was still in many of the actual legacy shaders, and that was actually disabling VRS. Okay, so where did we actually use VRS in Grid? As mentioned earlier, Intel supports tier 1, so we did it on a per draw call basis. And we took a fairly coarse-grained approach. Now this is all early work. This is the first iteration where we've used VRS in Grid, and we expect this work to continue during the next few months. But basically we apply VRS at different parts of the scene. We apply it to the environment maps, the mirrors, the road, and the main scene. And we can see a GPA capture done at fairly low quality settings to give you an idea of the comparable cost for each of those sections. Effectively, VRS is being applied to 40% of the total scene, with the other 60% still a fixed cost. That includes the global illumination, post-processing, and things like shadow generation that doesn't benefit from VRS. One important thing to note: when we first applied VRS to Grid, we realised we could actually have too much of a good thing. We said at the start, the whole point of VRS is to smartly control rasterization so you get quality where you need it. If we can take an example scene like this one on the start grid and zoom in to look at certain parts of the scene, we can see the fine detail when rendering at 1 by 1 VRS rates for things like the bridge cables, or on the bottom right you can see the foliage for the trees. If you look at those same images just above them, when we turn on 4 by 4 VRS, we found that we were getting a quality drop around those fine lines on the bridge cables, and the foliage dropped in quality significantly. It turns out both of these had something in common. Rather than the fine detail being generated by the triangle geometry, it was actually coming from alpha tested triangles. It turned out there was a relatively easy fix we could do for this. Grid has a depth prepass, as long as that was run at 1 by 1 VRS settings, and then while doing the forward plus pass we would actually disable alpha testing and made everything work as depth equals. Not only were we actually saving overdraw, but we also got the actual visual quality back because the depth testing was done where we would expect. So how does it actually look? Probably the easiest thing to do is a side-by-side video. So on the left we have Grid running with VRS off, and on the right we have VRS on. I'll start the video running now. Hopefully that video showed just how difficult it is to detect the difference between VRS on and off on a moving image, which is why at the start I said it was quite a good idea to take static screen grabs using a tool such as GPA. If you've got static screen grabs to compare, then you can start to look at using techniques such as using the peak signal to noise ratio to quantify the visual difference introduced by VRS. Peak signal to noise ratio is often used to compare things like compression algorithms and video codecs. More details can be found at this particular Wikipedia page. The one thing that's worth mentioning before we look at using peak signal to noise ratio in GRID is the range of numbers you'd expect to get and what is considered good and what's considered bad. With peak signal to noise ratio, if the images were identical, the peak signal to noise ratio would actually be infinity. With a peak signal to noise ratio in the high 40s or near 50, the images would be very hard to tell apart by the naked eye. As the number starts to then drop into the lower 30s, that is when you'll start to notice significant visual differences. So moving on to actually look at GRID. Here are 4 images, each taken at a different VRS level. You can see that measuring the peak signal to noise ratio on each of these images against the ground truth has a peak signal to noise ratio of between 45 when you have a VRS of just 1:2, down to 35 when we have a VRS level of 4:4. Using those same static images and a paint program, you can actually do a visual difference between them and actually highlight the differences between each image. And as expected, at the lower VRS levels, there are very few differences in the image. As you move up the VRS levels, you start to see more artifacts introduced. It starts to become noticeable when you get to something like 4:2, and certainly by 4:4 you can start to see differences in the image around the car and the buildings and the crowd in the distance. One interesting thing to do is to compare the peak signal to noise ratio of something like upscaling compared to applying VRS. One way to do that would be to pick settings that give very similar frame rates and then look at the peak signal to noise ratios, and that's what we've done here. We found that rendering the screen at 83% of its native resolution, then upscaling, gave a very similar frame rate to applying 2:2 VRS. If we took screen grabs and then actually looked at the difference, you can see that the peak signal to noise ratio with upscaling was around about 35, where with VRS it was 43.3. Almost identical frame rates. If we zoom in so we can actually look more closely on what's actually causing that, looking at the car and now going to the actual difference images, it's exactly what you'd expect. Upscaling tends to create blurring around the edges of the car and things like the crowd in the distance, where with VRS, because you're still doing the depth testing at the native resolution, the edges of the car and the crowd are still really crisp. The differences are only where the textures are varying on a per pixel basis. One area to pay particular attention to is full screen sampling artifacts. And the best way to explain this is using something like a full screen shadow mask. I've got an image here taken directly from the game where we zoom in to a small 64:64 image, and you can see here what would happen if we were to reduce the VRS rate to 4:4. So at high resolution, the data in the shadow map matches 1:1 with the albedo texture, and you can see that the outline of the character corresponds to differences in the full screen shadow map. If we were to actually sample the shadow map at 4:4, it obviously quantizes the results significantly. Whereas when rendering the characters, the depth information will still be identical, but when it's actually sampling the actual full screen shadow mask, you could be picking up results outside of the actual character itself and actually referencing geometry in the distance. Where we actually see this most obviously in GRID is when rendering the road surface itself, where there are very small artifacts that come from sampling the road, which should be in shadow, but when actually referencing the full screen shadow map, the sample point turns out to be just about on the car. At high resolutions, the full screen shadow map actually says that should be in light. So we get slight artifacts around the very edges of the car. And we're looking at ways to actually mitigate that at the moment. One area where we found VRS worked very well in Grid are the off-screen surfaces. Things like the faces of the cube map used for the reflections and the mirrors for the car. These tended to work very well because when applied to the actual scene, it was the high contrast areas that you were noticing rather than the fine detail. And the contrast tended to come from the actual geometric detail in the actual scene. You can see here that by applying 4x4, the image looks very similar, but we actually saved nearly 50% of the render cost. That has a few implications for Grid, where normally, depending on the quality setting and the hardware you're running on, you're only able to update a couple of the faces of the reflection map at any one time. With VRS, you have the ability to potentially apply far more. There's also a few other side benefits to look at going forward. Thinking back to David's part of the talk earlier when we were looking at async compute. While rendering the environment maps, we tend to do the shadow mask generation in parallel. At 1x1 VRS, the pixel shader is still relatively heavy. That means it's fighting for resources with the actual compute shader doing the shadow mask generation. And you can see here that while the pixel shaders are running, the shadow mask generation doesn't get a lot of time on the actual GPU. By changing to a 4x4 VRS, we can reduce the pixel shader cost and allow better load balancing for that particular part of the scene. To actually see what that actually means in game, I've got a couple of different images here. The reference is with no reflection map actually applied to the car. It's just simply grayed out. Where at the bottom on the left we have a 1x1 environment map, and on the right we have a 4x4. Very hard to tell the difference, and if I zoom in and just highlight the one area on the bonnet of the car, this is where the environment map is actually making a difference. You can see that different parts of the scene is actually reflected in the bonnet, and it's the contrast between the parts that show the sky and the buildings that really come out in the bonnet. And there's very little difference to tell between the 1x1 and the 4x4. And that's done at a 50% saving in terms of render time. We're only applying VRS just to the generation of that environment map in this particular image, just to keep everything nice and simple. One other area that is worth talking about is the terrain. At the start we mentioned that for Grid we've concentrated on the tier 1 VRS, which means changing the VRS rate on a per object basis. That works very well for most things in Grid, which tend to be fairly small and are fairly local in space. But the road is a unique case. It covers a very large part of the screen. And we found that we wanted to apply different VRS rates depending on which part of the road we were looking at. In the distance, we want a very low VRS rate, otherwise we get aliasing from the shadows, where we could apply a very high VRS rate on the road near the actual camera. We could have gone and asked the artist to break up the geometry into smaller chunks. We didn't want to do that, so instead we took a different approach. We effectively draw the road twice, and we introduce a geometry shader. On the first draw of the road, the geometry shader will call all the near polygons, allowing us to apply that 1x1 VRS rate in the distance. Then we rerun the actual draw call, toggle the comparison in the geometry shader, and render the triangles nearer the camera at a high VRS rate. There are other ways to do that. We could have used a compute shader to actually do geometry culling and sorting, and then generate draw indirect calls. So there is more than one way to do this, but it shows you don't have to necessarily change the actual artwork to make use of tier 1 VRS. And that's what it actually looks like with 4x4 applied to the road. A couple of other things worth mentioning. Most of the numbers we've given so far apply to Grid running on a 15 watt laptop. So we've been generally talking about 1080p resolutions. VRS is also very applicable when the resolution starts to scale up. And it makes a great deal of sense when you think about what we're actually doing with the VRS. At higher resolutions, pixels tend to be more similar in screen space, and you're much less likely to have very small triangles. and this is borne out in the numbers from GPA. If we compare the same image rendered at 1080p and 4K and look at the number of pixel shader invocations, as we go up through the different VRS rates at 1080p, you can see the savings. But at 4K, at pretty much every single level, we're actually saving more pixel shader invocations, but the mileage will vary on scene to scene. The other thing to bear in mind, not only is it more efficient, relatively speaking, at the high resolutions, the peak signal to noise ratio also improves. Because as mentioned, smaller pixels tend to have less variation between neighbouring screen texels, and therefore the peak signal to noise ratio is more likely to remain high. And finally, to summarise all the VRS work, for grid, as we've been talking through here, you can see we actually decided to apply different VRS levels to different parts of the scene. For the mirrors and the reflections, we applied 4x4. For the road, we split it between far at 1x1 and near at 4x4. And for the main scene, we applied 2x2. There are some objects, especially very small objects like the balloons, that we don't actually apply any VRS to. They tend to be very small, almost per pixel triangles, so they wouldn't benefit from VRS, and they add to the scene quality. Looking at performance, we see rather different numbers between daytime and nighttime, and that's because during the daytime there is a higher fixed cost to the scene because we are rendering things like the cascaded shadow maps, where at night we don't need to render the shadow maps, and instead we're spending more time on the per pixel lighting on the objects like the car and the road due to the number of local lights. Looking at the actual numbers, using our custom settings, we tend to get somewhere around about 14% gain during daytime and well over 30% at night. That means at night we're actually faster than rendering at a lower resolution, and we have better peak signal to noise ratios. At daytime, it's fairly similar between using VRS and upscaling in terms of the performance, but we do see slightly better peak signal to noise ratios as well. And with that, I'll hand you back over to David for the next part.
In this last section, I'm going to talk a little about asymmetric multi-adapter rendering. Traditionally, multi-GPU rendering has been very symmetrical. It required very similar, if not identical hardware, and the workload was split down the middle with the GPUs in the system all doing the same work, but perhaps on different sections of the screen, or on separate frames. The level of control that DirectX 12 brings changed this situation. It's now possible to specify exactly what gets processed where and when. This means that we can now take advantage of the millions of integrated GPUs that are sat doing very little next to a dedicated card working as hard as it can. There are generally about 3 ways of approaching multi-adapter rendering. The traditional approach is to split the workload evenly between the available GPUs, perhaps with one taking one half of the image and the other taking the other, or maybe it would be one processing one frame and the other processing the next. Another way that has become possible due to the increased control available is to offload some of the post-processing work onto the other GPU. This could work, but it does come with the requirement of copying all the buffers across the PCI Express bus, both to and from the integrated device. There's a third class of workload that lends itself to asymmetric multi-GPU work, and that's that of the producer-consumer model. That is, the integrated part produces some result that is then consumed by the dedicated card. This works even better if we can add a frame of latency to ensure that the two GPUs don't have to wait for each other to finish. It's this approach that we took and applied to the compute shaders that get executed right at the start of the frame to update the global illumination system. As I mentioned in the frame breakdown, the global illumination system works by having some volume textures attached to the camera. These then get updated at the start of the frame every time the data inside becomes stale. We also then run another task to blur the data a little to hide some artifacts that can occasionally be seen in the final image. The volume data consists of 3 128 by 16 by 128 half-4s, which hold the spherical harmonics values, and another integer volume of the same dimensions that contain some indices. The approach we took to performing and synchronizing the work is as follows. The compute shader waits for its previous result to finish copying to the other device. The copy queue must wait both for the compute shader to finish writing the source values and the renderer to finish reading the destination buffer, and the renderer then just needs to make sure that the copy queue has finished copying the values it needs to consume. Simple, right? Well, it's not quite that easy. as usually is the case, there's actually a bit more to it than that. All of the synchronization can stay the same, but there are restrictions on what types of resources can be shared across the device, and 3D textures can't. To work around this, in addition to the usual volume textures, we create some simple byte buffers that can be copied between devices. The producer then computes its result into its volume texture, and that texture gets copied into the producer's byte buffer. When that's complete, one of the GPUs copies the producer's byte buffer into the one belonging to the consumer, and then the consumer copies that buffer into its texture. Using a tool like GPU View, it's possible to look at the timing between the various queues. If all has gone to plan, then the compute queue, the copy queue, and the render queue are all running in parallel, and the frame's time will be determined by the last queue to finish. If all the synchronization is correct, that should be the work being executed on the graphics queue of the main GPU. If it's not, then things will probably need to be rearranged so that the multi-adapter work isn't delaying anything. We should also now see that our render queue duration is shorter than before we moved the work to the other adapter, giving us a performance gain. You might find that if the workload on the integrated adapter is intermittent, then it will throttle its clock rate down to save power and produce less heat. In situations like ours, this could result in lower performance and the main GPU having to wait for the offloaded work to complete. Intel have an extension which is present in all public drivers and will allow you to specify that the GPU should remain running at full speed. The takeaway from this is that asymmetric multi-adapter work is best suited for situations where the main GPU is saturated. If this isn't the case, then it can just do the work. The task is of producer-consumer type and can completely offloaded so that the synchronization and cross-device copying don't get in the way and dilute the gains. And the main GPU isn't sat around waiting for the result, otherwise it could just do the work itself. This is easiest to achieve if the computation can be done in a different frame. Luckily, many async compute tasks fit this profile. When planning work, you should be aware of what you will need from the PCI Express bus. There's a limited amount of bandwidth available, and this has to be shared with the rest of your game and whatever else the user happens to be running at the time. PCI Express Gen 3 by 16 has 16 GB per second available, and our data is only around 6 MB. This means that we could copy the data across the bus 2,600 times per second before it's saturated. So in this instance, the PCI Express bus is unlikely to become a bottleneck. But if more needs to be copied, this could potentially become an issue. It's best to minimise the size of the data that's transferred across the PCI Express bus. Splitting data by usage, much like you should with constant buffers, helps minimise the amount that needs to be copied. For some reason, using create committed resource doesn't seem as tolerant as separate calls to create heap and create placed resource. Some resource descriptions fail when passed to create committed resource that work fine when the equivalent descriptions are given to create heap and create placed resource. The steps listed on this slide are what I found work best. First, figure out how big the resource needs to be. Next, create a shared heap large enough to hold it. Create a handle to that heap, and create a view of the heap with the other device using the handle and open shared handle. Then on both devices, create a placed resource into the same place in their own view of the shared heap, making sure to use exactly the same description. And here are a few other things I noticed along the way. The first thing I recommend doing is adding the device that created a resource to its debug name. I found this to be the single most useful thing I did to highlight issues with the multi-adapter code. It will help you see which device queue is having issues, or maybe even which resource you're trying to use on the wrong device. I noticed that if you do use a resource on the wrong device, then D3D tends to report the resource as having already been deleted. This could be because it's likely to have a different virtual address and therefore can't be found in D3D's tables when doing the debug checks. Both of these tips are useless without the debug runtime, so switch it on. Right now, none of the frame capture tools I tried work properly, but GPU View and Intel's GPA Trace capture do. These can help figure out if synchronization is working the way it should, and they make it very easy to see one queue holding up the others on the timeline. And that's it from me.
Thank you, David, and that just leaves us to do the summary for today's talk. To summarise, with DirectX 12 take nothing for granted, especially regarding memory. Stress test early and on as wide a range of hardware as possible. Include lots of different hardware vendors, as that is a good way to trap undefined behaviour within the game engine. As David mentioned, we also found the Forward Plus proved to be both flexible and allowing for good async gains, especially at the start of the game's frame. We also found VRS to be a good fit for the Grid Forward Plus engine, allowing for smarter use of pixel shaders, especially at night where we got some fairly significant gains. It's also important to note that VRS is also compatible with other optimizations like upscaling. And finally, multi-adapter, while still a work in progress, is a natural extension of any producer-consumer workload, especially where latency can be hidden, allowing for smoother frame rates and or better image quality. If you download the PDF version of this talk, you'll also find several references to the various talks that were mentioned at different points. And finally, I'd just like to say thanks to the people both at Codemasters and Intel that made this talk possible. I hope you found it useful and have enjoyed the session. Thank you very much.